Here, for the first time anywhere, the turbine generators of a municipally owned power plant are using steam produced by nuclear energy for the generation of electricity. A nuclear reactor is taking over a substantial portion of the plant's coal-fired production to serve the power needs of 6,000 homes, 83 factories, and 102 miles of streets in Piqua, Ohio, a city of 20,000 people close to the metropolitan area of Dayton. Heat produced by fission in the Piqua nuclear power facility on the east bank of the Miami River converts feed water into 550-degree Fahrenheit steam, which is piped across the river on a specially constructed bridge and delivered at a pressure of 430 pounds per square inch to the municipal power plant to produce 11,400 net kilowatts of electricity. The Piqua facility is part of 10 reactors in the Atomic Energy Commission's Power Demonstration Reactor Program, another milestone leading toward the development of economic nuclear power operations and related goals of scientific, industrial, and social significance. The Piqua reactor is unique in a number of respects, but is particularly notable for its heat transfer concept, which centers around the use of an organic coolant. All nuclear reactors are essentially the same in principle. A fuel core of uranium, slightly enriched with U-235, produces heat through the neutron bombardment and fission of uranium atoms. The activity is regulated by control rods and occurs in a pool of circulating coolant. The Piqua facility and all of its predecessors in the AEC Power Demonstration Reactor Program consists of a reactor vessel of fuel elements and control rods, a liquid heat transfer system, and a variety of auxiliary systems to support, control, and protect the activity. Thus far, the principal difference between the reactors has centered around the method of heat transfer. The possibility of using a high boiling point organic liquid as both coolant and moderator was foreseen during the earliest days of nuclear reactor design. Radiation studies in recent years pointed to certain aromatic hydrocarbons in the polyphenol family as being adequately stable for use in nuclear reactors. An organic moderated reactor was designed and built for the Commission by Atomics International, a division of North American Aviation, at the National Reactor Testing Station near Idaho Falls, Idaho. The reactor attained criticality and began operation in September 1957. Full power operation of the Organic Moderated Reactor Experiment, or OMRE facility, confirmed the soundness of the concept and basic reliability of the design. The experiment established the wax-like terraphenyl hydrocarbon compound as a reactor coolant with advantageous characteristics that included a high boiling point, which permits reactor operation at low pressures, multiple physical properties that enable the fluid to moderate and reflect neutrons and carry heat away from the surface of the fuel, inertness to most metals, including uranium, low induced radioactivity of both carbon and hydrogen, enabling the fluid to serve as a shield above the core. Encouraged by the operation of the OMRE test, the Commission accepted a proposal submitted by the city of Piqua for the AEC to finance construction of an organic moderated reactor that would supply a substantial part of the city's requirements for electric power and reduce the number of coal-fired boilers to standby status. Under this agreement, the AEC owns the reactor and sells steam to the municipal power plant at the same price as the cost of its own coal-generated steam. The reactor is operated by the municipal power system, and the city has the option to purchase the plant from the government after 5 years' operation for the AEC. Because of its experience with the OMRE reactor in Idaho and years of prior research on the organic reactor concept, Atomics International was given the contract to design and build the Piqua facility. Construction at the Piqua site began in September 1959 and was completed in 24 months. There were special problems, as there are with any industrial installation. But, in general, construction procedures followed customary patterns of the building trades. The Piqua facility has many construction features in common with petrochemical plants. The Piqua nuclear power facility, which achieved criticality in early 1963, is an 11,400 electrical kilowatt reactor. The facility is contained in two structures, a dome-shaped reactor building 73 feet in diameter and 123 feet high, and a three-story auxiliary building which houses the service areas, control rooms, and auxiliary process systems. Here, without the containment shell, is a scale model of the Piqua facility. The upper level of the reactor building contains the fuel handling cask, new fuel storage room, decontamination room, hot tool storage, air supply system, and a 30-ton polar crane. The process rooms below contain the main heat transfer loop, degasification and pressurization system, vent and relief system. Here, too, is a particulate removal system and a spent fuel storage pool. The principal function of the dome-shaped container is to protect the population and plant personnel in the unlikely event of a fission product release. Although the hazard is remote, the risk is further reduced because the reactor vessel and associated equipment is below ground level, where it is also shielded by earth. The reactor room, with its floor just 4 feet above ground level, is enclosed by the dome-like containment shell. The room is 73 feet in diameter, 68 feet high, and served by the polar crane, capable of lifting the 12-ton cover of the reactor. The crane can also perform lesser tasks, such as lifting equipment access port covers. Here, the fuel handling machine is shown adjacent to the reactor opening. Ordinary concrete, 18 inches thick, lines the inside of the steel shell above grade. 18-inch concrete is also used in the interior between the reactor room and the process cells, also along access corridors into the process rooms. Piping, heating and ventilating ducts, and electrical penetrations are brought out of the shell at a subgrade level, leading to the auxiliary building. Here, in a view of the cavity liner during construction, we can see some of the 10 nozzles which provide access to the reactor vessel for control rod leads, organic fluid, and thermocouples. The 9-foot cover plate of the vessel has no penetrations, a unique feature of the Piqua reactor. It is bolted to the vessel and sealed by a soft metal gasket. There are only 3 access openings in the containment shell. All meet the same pressure and radiation protection requirements as the shell. This is the access port for fuel and equipment. This is the personnel airlock, which connects the 2 buildings. The auxiliary building is a conventional 3-story insulated industrial structure. The top floor contains the control room, which is the nerve center of the entire facility. Also on this floor is the instrument repair shop. The second floor houses the ventilation equipment for the control room and the cable spreading area. Included on the first floor are the electrical switchgear, air compressors, emergency diesel generator, and batteries, change rooms, chemical and health physics lab, and administration area. All auxiliary process systems not in the reactor building are installed in the basement area. Process equipment in the basement of the auxiliary building includes the organic waste system, exhaust air filter system, coolant purification system, liquid and gaseous waste systems, and coolant drain tank. The coolant purification system, by means of distillation, removes organic products called high boilers and impurities. These materials are pumped to an insulated hold-up tank and allowed to decay for some period of time. The materials are sampled, then analyzed, and when determined sufficiently free of radioactivity, are burned in the waste-fired boiler. The flue gases from the burning process are passed through a filter system to remove any radioactive particles which may be present. This is done prior to releasing the gases to the atmosphere. The ventilation system provides for the filtration and monitoring of all exhaust air before it is discharged through the stack to the atmosphere. A radiation monitoring instrument continually samples the exhaust air in the stack. If the monitor indicates a high radioactivity level, the ventilation dampers for the reactor building are automatically closed, isolating the reactor building air system from the stack. Radioactively contaminated liquid waste is filtered and collected in a hold-up tank. A sample is taken, which is analyzed for radioactive materials. If found to be below the AEC's limits, it is discharged from the plant. A radiation detection instrument continuously monitors this discharge. Gaseous waste from the degasification system is passed through a radiation monitoring system and into hold-up tanks for decay before being released into the exhaust filter system. Structural shielding is also provided in the auxiliary building. A tour of the two buildings with their numerous floors, levels, and compartmentalized areas, or a close look at the intricate detail of the scale model, creates a feeling of immense complexity, which can be more easily understood by glancing at a schematic flow diagram. Here is the reactor, and we see that there is one main heat transfer loop with two pumps operating in parallel. The hot organic fluid produces steam from feed water, which is then converted into electric power by turbo generators. There is one auxiliary loop which serves the functions of degasification, pressurization, decay heat removal, and coolant purification. The reactor vessel is made of low-grade carbon steel and has an internal diameter of 7 1/2 feet, an overall height of 27 feet, and a wall thickness of about 2 inches. It is designed to meet applicable engineering codes for an internal pressure of 300 pounds per square inch and a temperature of 750 degrees Fahrenheit. Returning to the scale model, we can see how the core is positioned near the bottom of the reactor vessel. It consists of 85 fuel elements of slightly enriched uranium with 13 control safety rods. The core is surrounded by an annular thermal shield supported from a ledge inside the tank. Steel grid plates located above and below the core support and position the fuel elements and control rods. The organic fluid, which is a mixture of the terraphenyl isomers, enters the tank above the core and flows downward through the fuel elements into the lower plenum below the lower grid plate. It then flows upward through the annulus between the core tank and the thermal shield into the outlet plenum of the core tank, through the heat transfer loop, back to the reactor. The organic fluid fills all of the available space in the tank and, as noted earlier, serves as moderator, coolant, and reflector, as well as shielding for the core. This is one of the assembled fuel elements of the Piqua reactor. It has an outside diameter of 5 1/4 inches and a length of approximately 80 inches. The uranium is in the form of 2 concentric tubes. The inner and outer surfaces of each fuel tube are covered with finned aluminum cladding, twisted in a slight spiral. These fins provide increased surface area to improve heat transfer. The assembly of clad fuel tubes is positioned between 2 concentric stainless steel container tubes. The ends of the stainless steel tubes are fastened to end plugs, which fit into the upper and lower grid plates of the vessel. The uranium alloy in the fuel elements contains approximately 3.5% molybdenum and is enriched with a little less than 2% U-235. 13 control rods regulate the power level of the reactor. These rods and their drive mechanisms are immersed in the coolant and do not interfere with core refueling operations. The rods, actuated by magnetic jacks, are operated manually or automatically through a selector switch, which permits simultaneous movement of from 1 to 3 rods up or down in minute steps. Loss of power to the rods causes them all to fall into the core, automatically halting the nuclear reaction. During full power operation, the coolant is heated in the core within a range of 520 to 575 degrees Fahrenheit, absorbing 45.5 megawatts of heat from the core. At capacity load, the full flow of coolant is pumped through the superheater and boiler, where heat is transferred to the steam system. At partial loads, a portion of the coolant is bypassed around the boiler in the main coolant loop. Although the design pressure of the main coolant system is 300 pounds per square inch, the operating pressure is 120 psi at the reactor vessel tank inlet. The hydrocarbon coolant undergoes some polymerization or forming of new compounds in passing through the reactor, and some radioactive products are produced due to trace impurities in the commercial grade coolant. A side stream taken from the pressurized coolant loop is passed through a purification system and returned to the pressurizing loop, along with an added supply of fresh makeup coolant to replace the coolant removed. Residual polymers are burned in a waste-fired furnace, and the heat is used in the operation of the overall system. A degasification and pressurization system removes water, hydrogen, and other dissolved gases and provides for coolant expansion as well as pressure control. This is the control room of the Piqua nuclear power facility. It is here, amidst this array of sensitive, highly communicative instruments, that all critical functions of the nuclear power facility are remotely controlled. The nuclear instrumentation circuits measure, indicate, and record neutron flux over the entire operating range, starting from the subcritical source level. The plant control system permits operation of the reactor plant either automatically or by manual actuation in accordance with plant load demand. The protective system, consisting of alarm, setback, and scram circuits, safeguards the reactor against malfunctions and errors. The radiation monitoring system detects and records radiation levels in key areas of the reactor plant and building. Visual and audio alarms warn the operator of abnormal conditions in the facility. Unit installation of monitoring equipment and other instrumentation makes it possible to remove a complete assembly for service and replace it in a matter of seconds. All of the instruments in the control room are readily accessible for visual inspection and repair. The control room operator has an intercom system which enables him to hold two-way conversations with personnel in every work area throughout the facility. This organic moderated and cooled reactor at Piqua is unique in a number of respects. Because the organic coolant does not become radioactive, and as a result of other design features, it is safe and practical for men to work within the containment shell while the reactor is in operation. The reactor can be operated on one main coolant pump and still produce at least 60% of power. The Piqua reactor operates at low pressures, which permit the use of standard weight piping and thin-walled vessels. Because the coolant is non-corrosive, free of hazardous chemical reactions, and low in radioactivity, the reactor has been built of ordinary materials familiar to the petrochemical industries. Mild carbon steel, rather than stainless steel or nickel-plated steel, is used for vessels, piping, pumps, valves, and heat exchangers. The coolant, with its high boiling point, will not flash upon loss of system pressure, and pressure differentials prevent the steam system from becoming radioactive. These are the features which merited operational evaluation in the Commission's Power Demonstration Reactor Program and led to the building of the facility at Piqua. Many of these same features, of course, are inherent safety factors. By combining them with deliberately ultra-conservative construction, the Piqua facility is probably one of the safest industrial installations in Ohio. A health physicist is on hand at all times. A man standing against the outer shell will be exposed to less radioactivity from the reactor than from the luminous dial watch on his wrist. The Piqua design gives promise of being adaptable for use in central power plants, marine propulsion, and peaceful application in many situations. Piqua is by no means the end of the line in the Commission's Power Demonstration Reactor Program. There is still much to be learned and much to be gained by pressing forward on the frontiers of nuclear science. The Piqua facility, however, marks a notable milestone with the advent of a power reactor that is moderated and cooled by an organic compound.